Hello again, grade 11 students, and welcome to the third session of this chapter. This session will be the last one as for the course, in which we cover the electric force and the work done by electric force. Afterwards, I'm going to suggest some applications and exercises that you will have to solve. Then I'll add a fourth session which has nothing to do with the course, but just solving these applications. Okay, now here we go. So starting with the electric force, which we will call later Coulomb's law. Anyway, we just stick to the electric force now. We have talked before about the gravitational field and how a gravitational force is produced when we insert a test particle into the field. The same thing holds true here. When a test charge is introduced into a region of an electric field, it interacts with it by a force, a field force, known here as the electric force. Mathematically speaking, it's given by the equation F equals small q, the test charge, multiplied by the field E of capital Q. Now, unlike the mass, Q can either be positive or negative. So we have two options between F and E. If we go back to mathematics, two vectors, when they satisfy U equals KV, U and V are said to be collinear or parallel. But they can either be of the same sense or opposite senses depending on K. Over here, the same thing holds true. So, force F and E are collinear, they are parallel, but they are either of the same sense or opposite senses. It all depends on coefficient Q over here. If Q is positive, then F and E have the same sense. We'll see an example about that. If you look at the upper right side, the blue circle is charge capital Q. It is positive, therefore electric field lines are going outwards relative to it. Now introduce a test charge Q, small q, which is shown as a circle and inside it a positive sign. Now first, the electric field due to the charge which was present in the first place is this one, and it is going outwards. And since this small charge is positive, then the force resulting is collinear to the electric field. Same sense also. The second scenario is the same charge producing the same field which is going outwards. The electric field is drawn going out of the charge, but the test charge introduced is negative, therefore the force is opposite to the field. Got this point? Now let's take another example, another scenario when the main or the charge producing the field is negative. Notice the field lines shown in green are incoming, are going into the charge itself. So electric field lines are inwards. At the charge that we inserted here, which is shown as a circle and inside it a negative charge, okay, the force is opposite to the electric field, because when Q is negative, force and field have opposite senses. Whereas in this scenario here, the electric field is inwards because the main charge is negative. Now, introducing a positive charge, then F equals positive times E, then F and E will be of the same sense, and you can see that in the figure. Bottom line, we need to memorize the equation F equals QE as a vector. Now these vectors can either be collinear of the same sense or collinear with opposite senses. It all depends on the charge small q. Now, what is Coulomb's force or Coulomb's law? Coulomb's law is specifically when a point charge produces a field and another point charge interacts with it. So going to the equation, F1 on 2 equals Q2, the test charge that we inserted, multiplied by the field produced by Q1, which we call here E1. In magnitude, F equals Q times E. We added absolute values because we do not care about the signs of the charges, whether they are positive or negative. Now E1 is given by definition as KQ over R squared. Joining or combining all these terms together, we get the equation F1 on 2 equals K times Q1 times Q2 over D12 square. D12 stands for the distance between the centers of the two charges. Q1 and Q2 are the charges of the two particles we're considering, and this force is mainly known as the Coulomb's force. Now we have two different scenarios. If we have opposite signs of charge, not opposite charges, opposite signs, one is positive, the other is negative, we'll have attraction. But if we have same sign charges, we will have repulsion. This is not something surprising. We have seen it maybe in grade 10, and you have talked about it in chemistry in grade 8 as well. Let's go now to solve an application to make things, or to check an application, which, as I said before, you will have to solve next time. I will post a video including the solutions of all these applications. In application 3, which is the first application for this session, we have two charges, Q and QB, placed respectively at 2 points A and B. This is, by the way, nothing but the previous exercise that we have solved when we found the electric field of QA at point I and the influence of B, which is the electric field also of QB, at point I as well. Over here, we are just studying the force of A on B and the force of B on A. Represent the forces of interaction between the two charges. So this is a direct application of the Coulomb force or the electric force. So feel free to solve it by any method you prefer. Next video is going to be about the solution of this application. Then you can check your work. That's it for this application. Now we move on to the last part of this session. Now we move to section 7, which is work done by an electric force. First, before I start, it's important to mention that this part is an eliminated part. This part was eliminated and we are not supposed to study it. However, I always like to go over this section so that we understand a notion related to the units used here. We'll discuss this. At the end, I will remind you that this section isn't of great importance. Just study it so that you have an idea about it. We consider the case of a constant force or motion within a uniform electric field, which will produce a constant force. So as a particle or a charge moves from a point of level A, as you can see here, towards another level, which is B here, regardless of the path it follows, the work done by the electric force as we move from level A to level B, as you can read here, equals the charge itself multiplied by the potential difference from A to B. Now, A to B, initial minus final, which reminds me a lot by the work done by the gravitational force, which was mg, height initial minus height final. And this is something nice so that you can always keep an analogy between gravitational interaction and electric interaction. As for units, work being in joules, like any other energy or like any other work, that charge is in Coulomb, while the voltage is in volts. So far, nothing new here. Now, this section, section 8, is a continuation of the previous section. And this is the main deal. When I told you that the importance of the work done by an electric force is to introduce a notion used in a notion of energy, or a unit used in energy, this is what I meant. The electron volt. Work is Q times U. If you express work in electron volt, then you would be expressing the charge in terms of electric units, which is E, as we have seen in chemistry in grade 9, I guess, where 1E is 1.6 10 minus 19 Coulomb, and voltage is regularly in volts. Thus, you will have the electron volt. Now, what's the importance of the electron volt? The electron volt is a unit which is widely used on the atomic scale in atomic physics or also in nuclear physics. 1 electron volt is 1.6 times 10 minus 19 joules. Now, other forms of this unit or derivatives are, or powers in fact, is the kilo electron volt, also known as the keV, which is 1000 electron volt, and we have the MeV, the mega electron volt. And the mega electron volt is used a lot in nuclear physics and radioactive reactions, if you have heard about them. Okay? By this, we seal the main ideas in this chapter. Concerning work and energy, work of an electric force, it's not important. The important part is understanding only what would an electron volt stand for. Now, we'll go to an exercise. In these applications, we focus once on the work done by the electric force. In the other application, we focus on the unit electron volt. In application 4, we have a conventional nuclear reaction of uranium produces 200 mega electron volt, express this energy in joules. Straightforward. If you just refer to the previous slide, or later on for the cheat sheet that I'll provide at the end of this chapter, you can solve this by simple conversion. Application 5 is an application about the electric field and the work done by a uniform force. Even though the work, as I told you, is eliminated, however, I prefer to solve this just to get used to how to use the work energy theorem first, and to get the notion of the work done by an electric force, which is eliminated for grade 11, but you will study it later when you step into universities. So we are given a capacitor with A and B plates being charged, and the charges are shown. First question is the electric field E directed upwards or downwards? Calculate the potential difference VA VB. Apply the kinetic energy theorem between A and B to calculate the speed of M as it reaches point B. So part 3 is a direct application of the kinetic energy theorem, but applied with electric force here. This is a bit tricky exercise or application when it comes to the last part. Give it your best, try to solve it. Don't forget, next time we're gonna post a solution with all detailed explanation about all these applications. Now one more exercise, an additional exercise, focusing on the superposition principle, where we need to add electric field vectors. However, in this scenario here, the vectors are non-collinear. So we're given two charges, Q1 and Q2, placed at points A and B, which you can see in the figure. K is also given. First part, we need to characterize the electric fields produced by these charges. Now that is giving the point of application, line of action, sense, and magnitude, which is direct. Then determine the characteristics of the net electric field, in which we have to add the two vectors. Now, addition of vectors isn't that hard. However, over here, the vectors are non-collinear. That means adding them isn't as simple as what we have done in application 2. We need to use what we have learned in mathematics about adding vectors, which is the parallelogram rule or chaseless method, depending on what you prefer to use. Then, using some trigonometry in order to come up with the final result. Give it a try. When we meet in the upcoming session, which is going to be a problem-solving session, we will go over all the details concerning this additional exercise. By this, we have finished everything concerning the course of the electric field. Before we end this session and the chapter, I'll go with you to a cheat sheet or a summary sheet including the basic points of this chapter. So, summing things up, first we need to know the definition of the electric field. We need to know how to calculate the electric field of a point charge and to give other characteristics, such as the direction is always radial. As for the sense, it depends on the charge itself. Positive, then it is going outwards. Negative, then it is going inwards. Then, the electric field inside a capacitor is uniform, and the characteristics are also important. And when a test charge is placed within a region of an electric field, then an electric force is produced. This verifies once again the field theory, in which we have a field produced by a certain object. Place a test particle into that field, it will interact with it via a field force. From that, we also reach the Coulomb's force, which you can directly use, by the way, when you have two charges. So the force between two charges has a magnitude given by K, Q1, Q2 over R squared. You can use this directly, or this if you prefer. Then, we studied the work of an electric force, of a constant electric force, or the work done by an electric force when the electric field producing it is uniform. However, we do not need to know the equation. All we need to worry about here is what is the unit electron volt. which is a unit used on a small scale, and its value is 1.6 10 minus 19 joules. This is all concerning this chapter. I hope that it wasn't that hard and that long. Until we meet in the problem solving session, review these and stay safe.